Like Skipper said, my name is Brian Lang. I'm a partner and a data scientist at Datascope. Before I get rolling on this talk, which I'll do shortly because we've got a lot to cover, I just want to give you a heads up. The audience for this talk is really intended to be people who are sort of new to machine learning or have tinkered with it a little in the past but don't really feel like they have a sense of what's actually happening when they import something from scikit-learn. So if you're the kind of person who can spend an hour reading about gradient boosting online and understand everything that you're reading, this may not be the talk for you. Maybe a little sort of higher level than you would expect. Next door, one of the Pandas maintainers is talking about scikit-learn and Pandas data types, so if you want to take off, I won't take any offense. Last thing, this talk is kind of a survey. I'm trying to cover as many algorithms in the next 45 minutes as we reasonably can. So I'm going to gloss over some things. I'm going to move quickly. We could neckbeard out about a lot of the sort of details of these things and how they're implemented in code, but I'm going to try and sort of stay above that to give you a high-level understanding and hopefully inspire you to learn more about some of these methods. So I mentioned I'm a partner and a data scientist at Datascope. Datascope is a design or data science consultancy, but we kind of think of ourselves as a mixture of a few different kinds of firms. Something like a design firm, like an IDEO, something like a consulting firm, like an Accenture, something like an analytics firm, like a Palantir or IBM. Of course, we're a lot smaller and less well-known than all of those companies, but you kind of get the idea. What that really means is that I work with some really friggin' smart people, which is where I learned pretty much all of this stuff. My background is really more of a software one. I kind of stumbled across Datascope a few years ago and became really interested in the data science side of things and have been learning about machine learning and statistics and all that stuff along the way. So all that said, we're going to talk about classification algorithms today. So if you're not familiar, these are a technique from machine learning that can kind of be boiled down to, I have a distinct number of groups or buckets, and I have a bunch of data points, and I want to sort those into the correct bucket or the right group. Popular examples, one that I'm going to use a lot during the talk today, just because it's an easy one to kind of get your head around, is a spam filter. So you can think of a spam filter as you have data points or emails, right? And you need to classify them into, is this spam or is this not spam? And if you use Gmail these days, it's doing even more than that. It's a multi-class classifier, right? It's classifying it into, is this a promotional email or is this something you might actually want to read? Another popular example of a classification algorithm would be the sorting hat from Harry Potter. So it's taking whatever it can tell by sitting on top of your head and being a magical hat and using that data to try and sort you correctly into one of these four houses, right? So some things to know before we jump in. Classification is what's considered a supervised learning technique, which means that you need data that has labels with the correct answers on it before you can do this. You can't just say, here are my four groups, I'm going to throw a bunch of emails at you, you figure it out. You have to give these algorithms examples so that they can learn. Some terminology things, so I'm going to probably more or less interchangeably use the words feature, dimension, column, attribute. These are sort of, well, they're features of the data, right? They're things like, in the case of an email, what percentage of the email is all caps, or how many words are in the email, or they're like columns in a database. Whereas I'll use the words class, category, label, and these are your Harry Potter house, right? These are the groups that we're sorting things into. All right, one more caveat before we get started with the algorithm stuff. I'm going to talk about algorithms for the next 40 minutes or so, but, and I think a lot of times when people are first learning about machine learning stuff, there's a real emphasis on wanting to learn about all the algorithms because you look at the scikit-learn documentation and you're like, wow, look at all these different things I can do. Like, I want to know how all of them work and what the exact right one to choose is. But a lot of times when you're working on problems like this, gathering more data or making better use of the data that you have by selecting the right features or combining them in a creative way or pulling in data from a third source and sort of merging it in to make the data richer is actually going to produce sort of more drastic improvements than just switching from one algorithm to another. That's not always the case. It depends a lot on your problem. You're going to hear me say that phrase a lot over the next 40 minutes, but just something to keep in mind while we nerd out about all of these methods. Okay, so with all that said, let's look at our sort of toy problem for today. Here's a big scattered plot that I together of some emails. So I mentioned we'll do the spam filter thing. So the red dots here are spam emails, blue ones are not spam. And the two features that I'm choosing here to make this plot are the number of mentions of brand names in an email and the percent of the email body that is all caps. So in reality, you probably have a lot more information than this. But I'm going to flatten this down to 2 dimensions. You'll see people in machine learning do this a lot just because it's much easier to draw in 2D than it is to draw in 3D, and much, much easier than drawing in 4, 5, 6, 7 dimensions. So, so keep in mind that this is kind of an oversimplification, but this will help us sort of understand what's happening with some of these different methods. So I'm going to start with something called a linear discriminant method. And this is, so we're human beings with eyes and brains and pattern matching abilities, right? If we were to look at this image and try and the way that we might distinguish the spam emails from the not, we might say, well, what if we just kind of draw a line right here? And we say everything above that line is spam, and everything below that line is not spam. We would do a pretty good job, right? We would get one of these wrong. There's some savvy spammer in the bottom here who's figured out that a non-all caps email that's not just doesn't just say Gucci over and over again might actually get through a spam filter. But in classification, this line that we drew is what we would call a decision boundary. And the decision boundary is sort of the shape that determines which of these categories a data point is going to fall into. So we drew this one because we're reasonable people, but we could have drawn something like this. And for each decision boundary, we can quantify how good or bad that boundary is by looking at sort of how many did we get wrong, right? There's a lot of different ways to measure error, and that's something I don't have time to get into today. But in this case, if we drew this line, we're getting 5 emails wrong. If we draw this line, we're getting 4 emails wrong. The original one, we were only getting 1 wrong. So we can compare these lines to sort of determine what the best line is. And if you remember from middle school geometry, we can represent these lines using numbers, right? So if we have a point or an intercept and a slope, we can describe what that line is that we use to sort of determine the cutoff for is this spam or not. And those are called coefficients, right? Those numbers that determine the line. So if we plot those coefficients and how good or bad the line is in 3 dimensions, we get what's called an error surface. And you can actually see, or a map of terribleness, as I call it on the slide. So what we're trying to seek here is how do we come up with the least terrible line to divide this thing into spam and not spam? And I won't get into the sort of like extreme details of this, but one method for doing that is basically what's called gradient descent, which is kind of rolling a ball down that surface, finding the area where it settles into the least crappy line that we can find. There are other methods for doing this too, but gradient descent is kind of at the heart of a lot of machine learning methods. Not all of the ones we'll talk about today, but some of them. So you can read more about that if you're interested. Okay, cool. So what did we just do? We had some training data. I threw a few Python snippets into this thing. I'm probably going to go through them relatively quickly, but just to kind of describe how would you actually do this with code, right? So we have some training data, and in the case of Python, and particularly using scikit-learn, which is a popular machine learning library that I'm going to use in my examples today, you're usually going to have all of your feature information. So in this case, you can think of that as the XY coordinates of these things, or the for the emails, the percent all caps and the number of brand mentions. And then you'll have a separate one that has the labels for each of those points, such that the first label here matches up with the first point. Second label here matches up with the second point. And those labels are numbers in Python, but those numbers actually correspond to the classes or categories that we are looking to sort things into. So 1 in this case being not spam, 2 being spam. Okay. So we took that training data and we created a model out of it, right? In scikit-learn, you do this by importing whatever method you want to use. Of course, I picked one that has like the longest name in that entire library. From linear discriminant analysis, import linear discriminant analysis. That's the, anyway. So you create that model. Some of you are probably familiar with this, but just to give you sort of an example of how simple it is, you're feeding into fit then that x and y that we defined just before. So once you've called this, it actually changes that model object and saves the information that contains that boundary, or that defines that boundary in that object. So we actually have a trained model now that's entirely independent of the original training data that we used to train it. It's its own thing. If you were to take that model and save it, like for example, into a pickle file or something like that, it's not going to contain every email that we fed into it in the first place. It's going to contain enough to be able to make decisions, but not necessarily all of the training data itself. We have like an abstract idea of what spam is and isn't. So now, the exciting part is you have a new data point. You have a new email. You want to be able to mark it as spam or not, right? So you feed that into the model, and in Python that might look something like this. You have your new point. You call model.predict, pass the point in, print out the result, and it's 1, which if you remember is predicting that this email is not spam because it fell in the blue section of our model. So most of the time people aren't going to use a linear discriminant classifier. There are cases where if you need to train a bunch of classifiers for some reason, these are pretty quick. But there are better options these days, which we're going to get into now. I just use this as sort of a way to start getting you into this terminology and how I'm going to present the rest of these. So one of those that you might actually use is logistic regression. Again, there's more details here, but in practice it works a lot like what we just talked about, except for that instead of having that hard border of we drew a line through it, there's actually sort of a gradient between your two classes in the form of a logistic function. So, so there's shades of gray that a logistic regression provides that can be very helpful depending on the problem that you're working on. We'll talk about sort of how to select from the different algorithms that are at your disposal at the end. But in Python, the way you would do that, this is going to start to look very familiar. The great thing about scikit-learn is you just pull in that model from a different part of the package. The fit and work pretty much exactly the same. So that's pretty cool. Okay, support vector machines. I like to think of support vector machines like advanced to draw a line through it. And there's kind of two advancements that are relevant here. One of them is that they have a better definition of terrible than just the old school linear discriminant stuff that they were working on in the 50s and 60s. And the other problem that you may be thinking of is that toy problem I showed earlier. It was very easy to draw a line, and the data was shaped in such a way that that line divided things, right? But what if your data is not shaped in a way that you can draw a line through it? What if you have like a cluster of spam emails in the middle of the scatter plot and everything around it is not spam? It's going to be hard to draw a line. SVMs can handle this through transforming your data to a higher dimensional space. I'll show what that means right now. So here's an example of data in one dimension, right? So we just have numbers along a number line you can think about. And the way that this data is oriented, if we try to draw a line to separate it, we're going to have a bad time, right? We're going to, no matter which side we call blue and which side we call red, we're going to get 3 wrong here. We scoot it over here, we're still going to get 3 wrong. There's no way to divide this with a line. It's just not going to work. But without gathering any additional data per se, we can do a little bit of sort of a math trick on this in order to actually be able to divide this with a line. And in an SVM, that's the kernel trick. So kernel basically means you're transforming data from a lower dimension to a higher dimension. In this case, all I did to do this was pretend these are numbers, and we just take the square of each number, right? We just take the square of each number and assign that as a new feature. So now we're in a higher dimensional space. We transform that data. We didn't actually really add like any information per se. We just took the information we already had and augmented it. And now we can draw a line through it. So it's like magic. This was what people were really excited about this when they came up with this. Now, you can get much more advanced than this when you're talking about kernels. There's lots of really clever ways of getting outside of, or being able to handle things that aren't shaped like lines. So here's some plots I stole from the scikit-learn documentation. You can see some examples here. In the middle, this is a linear SVM, meaning there's no kernel really being applied. It's just dividing it with a line. And you can see it's really struggling with some of these shapes. And on the right here is what's called an RBF SVM, or radial basis function. That's probably one of the more popular kernels to use with a support vector machine. And you can see that it's creating these really complex shapes because of how it does the transformation. RBFs are really cool. I'd love to talk more about them today, but don't have time. But look into it, or maybe keep your eyes peeled for a future talk. The other thing I mentioned that SVMs do differently is a better definition of terrible. So if you remember that first problem I was showing you, you can draw a line through it like this, and we separate, we only get one wrong, this is a good line, right? We could have also drawn the line like this, or like this. And all of these would have had the same sort of terribleness rating, right? And so how do we decide between, we have all this empty space, and as you increase the dimensions of your data, there's going to be more and more empty space where you could potentially draw that line. How do you decide where in that empty space that you put the dividing line? Because you could put it right here, and this is right up against those blue data points. It seems like maybe that's not the best choice. So the other idea that SVMs introduced is this idea of a margin. The margin is the distance between the decision boundary and the closest point. So in this case, you can see the margin in yellow here. And if we move that line down towards the blue points, the margin's going to shrink. And now it's really skinny. And if we scoot that line up towards the top, the margin's going to grow. So in addition to having this ability to plug in kernels, SVMs also try to maximize the margin, which essentially means, in the absence of data, since we don't have any points in this sort of liminal space, I guess, try and put that dividing plane right in the middle. Just because we don't have any, if we update it later, we have more data points than we can handle, then we might move that boundary. But if we don't know, just stick it right in the middle. That's going to do better on higher dimensional stuff and instances where you have less data than a traditional linear discriminant. Okay, so doing this in Python. Again, pretty straightforward. Introducing for the first time here, you'll see that when you create the model, this is when you can kind of put in some of the parameters, the things that you can tune about any of these models. The ones I've showed so far didn't show those yet, but in this case, this is setting the kernel to be polynomial and the degree to be 2. That's exactly what I showed you earlier with squaring the thing, right? So that's something you could do. The most popular kernel probably for using an SVM is the RBF one, because you can read more about it, but it can handle all kinds of sort of wavy shapes, and it actually uses the data itself as the new space that you transform it into. It's kind of mind-breaking, but anyway, you can set that to whatever you like in there, and all that stuff's in the documentation. Okay, so let's get away from lines. There are other methods that you could come up with to sort things into categories, right? K-nearest neighbors is one of these. I think of K-nearest neighbors as kind of like the, on Amazon when you see like customers who bought X also bought Y. K-nearest neighbors is kind of that approach to classification. What does a similar case look like? And using that to infer like what you might call this email. So we have a new email up here, and we're just going to say, what's the nearest neighbor? What's the one nearest neighbor? Which meaning, what's the most similar email? Is it spam? So the most similar email to this email is spam, so we'll call this email spam. The K is referring to the fact that you could change that number, right? Increase K to 2, we're going to look at the 2 most similar emails and take the average of those. They're both spam, so this one's spam. One thing to be aware of with this is that tweaking that K really changes the properties in the boundary that come out of using a classifier like this. So if you have a really low K, like K equals 1, this point down here It's kind of unclear whether this spam email is an outlier or whether that's part of a broader pattern. We maybe don't have enough data to know. But the email that's right next to it is going to latch onto that and call it spam because it doesn't know any better. As you increase k equals 2. Now you have one spam and one not spam. Different KNN implementations deal with this in different ways. Sometimes you just say, well, whichever one is more common, we'll take that one. Sometimes you say, well, whichever one is more close, we'll take that one. But as you increase k, it becomes kind of less sensitive to those nuances in the data. And I have a figure in a second that will kind of demonstrate that. Another piece from the scikit-learn documentation, and you really can't see it on this screen. When you look at my slides later, there are figure attributions here. I didn't whip all of these up myself, but they're really instructive to look at. So you can see k nearest neighbors in the middle here. These are decision boundaries for KNN classifiers. And you can tell these are definitely not lines, right? It's handling very sort of complex shapes in the data, and it looks kind of jaggedy and funky compared to the linear SVM on the right, which can only draw a line through things. And then this is an example of, this is from a blog post from Burton de Wilde, a really great blog post on KNN if you want to learn more about it. But you can see on the left here is k equals 1, and then k equals 5, and then k equals 25 for the same classification problem. And if you look at that border, it's kind of, there's a smoothing effect as you increase the k. So you give up catching sort of like nuance in the data, but you're also less likely to focus in on something in your training set that was just kind of weird. It kind of goes from this weird sort of like island-looking coastline to something that's more smooth as you increase k. Okay, so doing this in scikit-learn is going to look a lot like the things that I've already showed. You set the number of neighbors as one of those knobs that you can tweak on the model, fit, predict, etc. All right, decision tree learners. So this is another approach, and this is kind of like if we were to look at this, these emails, and let's say we were going to make a flow chart for a human to look at this chart and be able to decide whether this email is spam or not, right? So the first thing we might do in making that flowchart, we want to sort of eliminate as many of those dots from the running as possible with one slice along one of the features. So in this case, we might say if x is greater than or is less than 3, I think I flipped my labels on there, but if x is less than 3, oh no, that's right. If x is less than 3, we know it's not spam. Whatever x is, right? This is some feature of the data that we came up with. And this is artificial. Your stuff's usually not going to look this clean. If it does, you're probably going to kick ass at classifying it. So that's our first cut, right? Everything left of this line we don't have to think about anymore. Our next one will be right here because we could say, okay, everything above this line, if y is greater than 4, then it's not spam. Here, if x is less than 5, then it's spam, right? And now we've sort of covered the entire space, and this is what our decision boundary looks like. So it's not a line, it's actually like a block, right? And the more freedom you give to a decision tree, it can make all kinds of little intricate chains of blocks and cuts and things like that. If you don't give it very much freedom or very much depth to the tree, then it's going to be sort of more macro shapes like this. Keep in mind, again, this is in 2D, and once you start to get into higher dimensional space, these are going to capture a lot more nuance than like a square. But squares in 7 dimensions look friggin' crazy. You can't even imagine what they look like, really. At least I can't. Maybe there's some mathematicians here, but okay. So so doing this in scikit-learn again, pull in the model, fit, predict. Another kind of cool thing that's unique about the decision tree, and particularly with scikit-learn, if you install PyDot, which is another library that allows you to draw these GraphViz visualizations, it'll actually spit out the literal flowchart that is what you trained on this model. Which, if you're using this to come up with something that's like more like an algorithm that's going to be executed by people, more like a heuristic, then this is actually really cool, right? And then I mentioned that if you give a decision tree a lot of freedom, it can really cut a bunch of different shapes and get very intricate. that's a blessing and a curse. It means that they're very prone to overfit on little nuances in your training data if you give them a lot of freedom. So in this case, up in that top left corner, you might not want to assume that every data point that you see up there is spam in the future. I didn't come up with the most egregious overfitting example here, but it's something to be aware of with those. I'll talk more about it at the end as well. Okay, one way you might compensate for that is with an ensemble model, and these are growing popular these days. Ensemble models, there's a bunch of different methods for doing this, but it really means making a bunch of models and combining them in some way. So the first one I'm going to talk about is bagging. And bagging basically means you're going to split your training set by randomly sampling it into smaller sets. You're going to train a model on each of those smaller sets. So in this case, let's train some decision trees. We end up with decision boundaries that look like this. So now we have 3 models. We have a new data point. We have a new email coming in. We want to say, is this spam or not? So we give that data point to every model. And each model says, that's not spam, or that's spam, or that's not spam. And then we take a majority vote, right? So if you look at this decision boundary in the middle, this is an example of a decision tree maybe overfitting on the training data that you gave it, right? It's calling this little region in the bottom left spam. But the other 2 don't, because they didn't have that point in their set, because they all have subsamples of your full data. So they're actually going to outvote that overfit problem in the middle model. Usually you're going to train a lot more than just 3 when you do an ensemble. That kind of depends on what method you're using, but our final answer here would be not spam. Another way to think of this is the decision boundary for a bagged classifier is really like the sum of the decision boundaries of its components. So if you lay them on top of each other, you end up with a shape that's much more nuanced and smoother than you would get if you just trained a decision tree on this overall. But there's lots of ways to do ensembles. Random Forest is one that you've maybe heard of because A, it's kind of a fun name. I think somebody should name their band Random Forest if they haven't already. But it's also grew popular, I don't know, probably in the last decade, I would say. It's kind of like bagging, but at each time that you are making those splits in your decision tree, you also constrain randomly the features you're allowed to make the split along. So this is sort of adding more randomness to the process in order to avoid making those overfits on these really sort of like corner cases in the training data. Because you might not, you're only allowing the tree to like pay attention to certain parts of the email, so it doesn't zero in on this one really weird email you got from your uncle or whatever. Extra trees stands for extremely randomized trees, and this is adding even more randomness, where not only are you splitting your training set and constraining the features, but you're also not even making the optimal split every time that you make a split for the decision tree. It's crazy to me that this works. I do need to do some more reading to understand why. But you compensate by training it with a ton of trees, right? So when you do extra trees, you have a super huge ensemble and can, despite the fact that you're not making optimal choices on each individual one, the aggregate of them are supposed to sort of catch some of the broader patterns in your data set. So these 2, depending on what your data looks like, this is really true of everything I'm talking about today, will have different performance characteristics. Sometimes one is better than the other. Sometimes one will be sort of more prone to focusing on an outlier, so it might do better at first, and then you put it into production, you realize, oh, I didn't properly test this, and it's overfitting. Some other ensemble methods, voting. So bagging kind of has a voting component, right? But you could imagine, rather than splitting your training set and training the same kind of model on all the subsets, what if you took your entire training set and just trained a bunch of different types of models? So you train a KNN classifier, you train an SVM, you train a decision tree, and then you have all of those different methods vote. You see this a lot in people who are trying to squeeze like the last few decimal places out of something. I think the winner of the Netflix prize voted like a bunch of models together. And I have a visual that will kind of show you what effect that has. It's kind of cool. Can help compensate for some of the weaknesses in each of the individual methods. Boosting is, I guess it's sort of an augmentation of an ensemble method. And boosting is really popular right now because it's can produce really good results. In boosting, when you're still training a set of models and taking the consensus of them, so let's say we're boosting with decision trees. You train the first tree, and because this is supervised learning, we know the correct answers. So we can look at the ones that the first tree got wrong. When you train the second tree, you overemphasize focusing on the ones that the first tree got wrong. When you train the third tree, you overemphasize the ones that the first two got wrong. So it's kind of cool because you're almost building a team of classifiers to work together and complement each other's like strengths and weakness, or really each other's weaknesses. And so you can imagine how that might result in sort of an ensemble that can perform better than just creating those things randomly. Okay, so this is another cool figure from the scikit-learn documentation showing the example of that voting classifier. So at the top you have a decision tree and a KNN, and then a kernel SVM. This looks like probably a polynomial one, but I'm not sure. And you can see these have their quirks, right? So the kernel SVM, because of the transformation, there's this kind of artifact in the bottom right where in this area where we haven't seen any data, for some reason it thinks it should be red. And the other classifiers don't see that way because that doesn't really, I don't know, make sense. And let's see, yeah, and then also on the sort of like middle left part, you can see the kernel SVM and the decision tree think that that area should be red where the KNN kind of like starts to recede for some reason. So these are kind of quirks of these different models. But then in the bottom right here is a voting classifier of all three of them. And you can see that because you're sort of using these different approaches, they are canceling out each other's sort of quirks or shortcomings. I mean, without having data in those areas, we actually don't know if they're shortcomings. Maybe that is, maybe the SVM is getting it correctly. But that's kind of an example of what voting can do for teaming up classifiers together. Of course, then that's more computation because now you got to train all these different models, and every time you do a classification, you have to call all of them. So that's one of the downsides, I guess. All of this stuff is in scikit-learn. Not going to get into the details, but rest assured the ensemble module has all of this stuff in it. So usually at this point, the question that I get is, okay, cool, so you just taught me about all of these things. Which one of these, what do I use? Which one of these do I pick? And the answer is that they'll perform differently on different data that has different characteristics. And so really, the safest method would be to test as many of them as you can, try out different parameters, and this is kind of the science part of data science in some ways. It's how do I experimentally verify that using this method over that method, or statistically verify, I guess, this method over that method is going to produce better results. That said, these classifiers have some different characteristics that might help you sort of point in the right direction when you're getting started. So a few of those, we talked about being able to draw boundaries that aren't lines. Providing probability estimates is another thing. Depending on, you could imagine if you are building an email application, you might want your spam filter to treat an email that you're 95% sure is spam different from one that you're like 51% sure is spam. And some of these models can also tell you how important the features that you fed into them are to the final result, which can be really nice when you're developing these models because you could throw out the ones that aren't any use. It might give you some intuition towards what features were really contributing or that kind of thing. So I'm going to kind of fly through these tables. I'll put these slides up so that you can look at them later. But logistic regression, you're stuck with a linear boundary, but they can provide probability estimates. And if you scale your data such that the features are on the same sort of magnitude, so you don't have like a percentage in one column and like millions of dollars in the other, then those coefficients of the line can actually give you a clue towards which of those features are most important, right? SVMs, they can do nonlinear, as we saw. They can't really provide probability estimates. You can kind of fake it, but it's very computationally intensive. And they can't really give you any feature importances. KNNs, absolutely nonlinear. You can kind of get probability. You're really getting more like shades of gray. But if you think about a k=5 classifier, it could tell you, well, 4 out of the 5 were spam, or 3 out of the 5 neighbors were spam. That's precisely a probability, but it does give you some more nuance than just yes or no. Don't really give you feature importances. Naive Bayes, I didn't cover in this talk. It's a probability-based way of building a classifier. And it's a little harder to visualize and fit into 45 minutes. But just for your reference on these tables, yes, they can do nonlinear. They're built on probabilities, so they're great at providing probabilities. And no, they can't really tell you how important a feature is to the model. Decision trees, yes, nonlinear, no probabilities. They can kind of give you importance based on how many times you made a slice in the flowchart along one feature or another, right? So in our example, we did it twice along the x-axis and only once along the y-axis. So that might tell you that if you had to throw one of those out, there's more information contained in the x-axis than the y. It's not perfect, but might give you some intuition. Ensemble models can do nonlinear, can kind of provide probability by knowing how many of the classifiers voted for the sort of resulting answer. And depending on their component parts, they can give you those importances. If you use things that can give you importances, it can give you importances. Boosted models, exactly the same. A couple other things when you're putting these into production that you might care about. Can you update them with new data without having to retrain from scratch? And are they easy to do in parallel on something like Spark, or even just if you have like a quad-core computer or something, you want to use all of those. Logistic regression, the answer to both of these is kind of. People have come up with methods for refitting an existing logistic regression model and for training them in parallel. They won't perform identically to if you just retrain from scratch, or if you train one on a single machine rather than in parallel. But it'll kind of work if you need it to. SVMs depends on your kernel. An RBF is a tricky thing to update with new data because the space that you transform your data up into depends on the data itself. So when you get new data, that space changes. So you can't really just kind of like barely move that line a little bit. You kind of have to restart from scratch. But if you're just doing something like a polynomial, like I was showing with squaring things, or even just a linear one, like you just want it to be a really good straight line, those you can refit. Parallelizing, again, the RBF is kind of difficult to do across many machines or take advantage of that. But other kernels, that's not as hard. KNNs are great for both of these. You can imagine parallelizing. You just split your data set across a bunch of computers and they all return the sort of closest neighbors, and then you can figure it out from there. And they're very easy to update with new data because you're just, the model is essentially the points and the distance between them. Naive Bayes, also great for both of these. They're probability based, so they're really just counts, and they're easy to update using Bayes' rule. Decision trees, not very good for both of these things. They're hard to update because as soon as you have new data, that split that you made originally might not be the optimal one anymore. They're kind of hard to parallelize, but they're really fast to train. So that kind of makes up for it in practice because you can just train a bunch of them in an ensemble or just one if that's what you're doing. Ensemble models, you can kind of update them with new data because if you have, 100 decision trees that you're calling on to make the decision for you, you have new data. The old trees might not necessarily take advantage of the new label. They don't take advantage of the new labeled data, but you could train some new trees that do and add them to the ensemble. It's kind of an art figuring out how you might adapt that over time. Do you throw out the old ones? Do you just end up with thousands of decision trees? But it's, in theory, kind of possible if you really need to do that. And they're easy to parallelize, right? Because you're doing exactly the same thing on small subsets of the data. Very easy to farm out on a cluster or just across the cores of your computer. Boosted models, same story with updating them, but they're harder to parallelize because if you remember, you have to do things in order with a boosted model. You have to know how well the first one did in order to train the second one. And then you have to know how well the second one and the first one did to train the third one. So harder to do. Now, in Spark, there are methods to do pretty much all of this stuff on like a Spark cluster, but they're not all necessarily going to take advantage of the fact that you're doing it across many machines or many processors. Okay, so I got to wrap up, but some other quirks. Keep in mind with an SVM, picking a different kernel will have a lot of impact on how your classifier performs. In KNN, you have to define what similarity is. That's something that I glossed over, but it makes a big difference depending on the type of data that you have. The other thing about KNNs is that they're what are called lazy learners. They're very fast to train, and they're very, well, comparatively slow. They're still computers, right? Comparatively slow to classify. Compared to other methods. Can be good, can be bad, depending on your application. Naive Bayes, you have to choose a distribution. Another cool thing about Naive Bayes is that they can deal with like nulls, basically, when you're missing a feature for a data point. Decision trees, we mentioned both of these things already, right? You can get literal flowcharts out of them, and they're very sensitive to outliers. Ensemble models, they're less prone to overfitting than their component parts, which is pretty cool. It kind of allows you to make use of decision trees where you have to be really careful if you're just training one. If you make 100 or 200 of them, they can kind of compensate for each other. Boosted models, they have more parameters to tweak than an ensemble, right? And they're also slightly more prone to overfit than an ensemble. But if you tune those things correctly, they can perform better than an ensemble. So this is why when you see sort of the most popular Kaggle winners who are squeezing out the last few decimal points of an analysis, a lot of times they're using some crazy boosted model or some voting algorithm of many boosted models or things like that. So in practice, my personal opinion is that's not always necessarily what you care about. There are lots of these other properties, such as being able to parallelize something, being able to explain it to your boss, that might matter more than squeezing out the last decimal point, but it's just something to be aware of if accuracy is like of the utmost importance. Okay, so I didn't leave a lot of time for questions, but it's lunchtime now, so I'll stick around. I'm happy to talk about this stuff. It's really fun. Thanks for listening to my talk.